Now let's talk about the expectation of a discrete random variable. The definition of the expectation of a discrete random variable can be seen right here. It is basically the sum of x times px over all the possible values of x. And you can think of the expectation as the value that the random variable takes on average, or the value you are expecting the random variable to take. But you should take that with a grain of salt, because as we're going to see later, it may be a value that the random variable cannot actually take. So one of the most important formulas that one should remember is that the expectation of any function of x can be written like this. Now the proof of this is not trivial, but here's a sketch of it. So you start by defining this random variable y, which is equal to g of the random variable x, and then you realize that the expectation of g of x is nothing more but the expectation of y. So now you are allowed to use the formula that we use as the definition of the expectation of a random variable for y this time, and you get this. And then here you can use the theorem that transforms the probability mass functions to rewrite p of y. So when you do that, you're gonna get, instead of p of y, you're gonna get the sum over x inside the set of values that give you y when you pass them through g, and times p of x. And then you can rearrange the summation. So you're going to write sum y, sum x in g minus 1y of y p of x. And then if you meditate a little bit on this expression, you will see that it is nothing more than this expression. And this proves the result. Equipped with the previous theorem, we can now start proving a lot of useful things about expectations. So this is also a very common formula that states that the expectation of x plus a constant is the expectation of x plus that constant. So to prove that, we basically just write down the formula that gives us the expectation of x plus c using the result we obtained in the previous slide. This can be written as the sum of x plus c times p of x, and of course this can be broken down into a sum that is like this plus a sum that is like this. Now here the first term is nothing more but the expectation of x, and the second term, you can take out the constant c and you can rewrite it like this, but then you realize that this sum over here should be 1, because this is the sum of the probability mass function over all the possible values of that variable, and that should be 1. And this constitutes the proof of this theorem. Now here's another useful formula that says that the expectation of lambda times x, where lambda is any constant, is lambda times the expectation of x. And the proof of this is very similar to the previous proof that we just did. So the expectation of lambda times x is by definition, or if you like by the theorem that we just proved a couple of slides ago, it is like this: lambda times x times p of x, sum over all the possible values of x. Lambda is a constant, you can take it out of the sum, so it is written like that. And then on the rightmost term, you recognize the expectation of x, and that is pretty much it.